Hello, and welcome to this Math 23 lecture video on parametric surfaces and surfaces of revolution. This lecture video consists of 3 parts, and this is the first of them. Recall from Math 22 that curves in 2 and 3-dimensional space may be represented either by a set of parametric equations in some parameter, usually t, or by a vector-valued function in the variable t. In this video, we explore how surfaces in 3-dimensional space may also be represented by a set of parametric equations, but this time in 2 parameters, say u and v. At the same time, surfaces may also be viewed as a graph of vector-valued functions, but in 2 variables u and v. I'm sure you're now excited to learn more. So, let's start. Consider the vector-valued function r in 2 variables u and v with components x of uv, y of uv, z of uv, which we can also write as x of uv I hat plus y of uv j hat plus z of uv k hat, defined on some region D in the uv plane. By a parametric surface, we will mean all points x, y, z in 3-dimensional space such that your x is equal to x of uv, y is equal to y of uv, and z is equal to z of uv, where uv is any point in the domain D of the vector-valued function r. To visualize what is happening, suppose the domain D of the vector-valued function r of uv is this region in the uv plane. Applying the vector function r on a point uv in D results to a vector r of uv in 3-dimensional space, whose position representation is shown here as this pink vector. The head of this vector is a point on the parametric surface S associated to the vector-valued function r. Running through all possible points uv in D will yield different vectors r of uv, and the surface traced out by the tip of the position representations of all possible vectors r of uv is exactly the parametric surface S. We say that r of uv is the vector equation of the parametric surface S, while the equations x equals x of uv, y equals y of uv, and z equals z of uv, the parametric equations of S. Note that both forms yield the same graph. The only difference is that in the vector equation of S, the parametric surface S is obtained by considering only the heads of the position representations of every vector in the range of the vector-valued function r. Next, we consider constant curves, which provide us a way to visualize and analyze parametric surfaces. Suppose we fix u to be the constant u0. The graph of u equals u0 in this uv plane is this blue vertical line. Applying r to each point of this line yields this blue curve that lies on the parametric surface S, called a constant u curve. This is because setting u equals u0 in r of uv results to r of u0v, which is now a vector-valued function only in one parameter v, whose graph, if you recall from Math 22, is a curve. Similarly, setting v to be the constant v0 results to the curve r of uv0 that lies on the parametric surface S. This curve is called a constant v-curve. In the figure, the red horizontal line is the graph of v equals v0 in the UV plane, whose image under R is this red curve on the parametric surface. Finally, drawing different constant U curves and constant V curves on the parametric surface S, such as shown here, induces a partition of S into so-called patches of the parametric surface S. We now illustrate these concepts with the following examples. In this example, we are asked to sketch a portion of the parametric surface with vector equation R of uv equals u plus 2v, u minus v plus 3, and 2u plus v. The best way to identify the parametric surface is to obtain a Cartesian equation with the surface, that is, an equation in x, y, and z. We start by writing the vector equation in parametric form. That is, we have x to be equal to u plus 2v. We have y to be equal to u minus v plus 3. And we have z to be equal to 2u plus v. Hence, we obtain a system of three equations. Remember that our goal is to find an equation in x, y, and z. And so, we proceed to eliminate the parameters u and v. From the first and third equation, we have negative 2x plus z is equal to negative 3v. Isolating v, we obtain that v is equal to 2x minus z all over 3. Substituting this expression for v in the first equation, we get u is equal to x minus 2 multiplied by 2x minus z all over 3. Simplifying, we obtain that u is equal to negative x plus 2z all over 3. We can now plug in these expressions for u and v in the second equation to get y equals negative x plus 2z all over 3 minus 2x minus z all over 3 plus 3. Multiplying both sides of the equation by 3, we have 3y equals negative x plus 2z minus 2x plus z plus 9. Simplifying, we obtain 3x plus 3y minus 3z is equal to 9. Thus, we get the Cartesian equation for the parametric surface to be x plus y minus z is equal to 3. Another way to obtain the same Cartesian equation is to notice that adding the first two equations yield x plus y is equal to 2u plus v plus 3. Since 2u plus v is equal to z, we immediately obtain this same equation. Now, this equation should look familiar from Math 22. Indeed, this is a linear equation in x, y, and z, and so its graph is a plane. Recall that one way to sketch a portion of this plane is to identify the intercepts of the plane. To obtain the x-intercept, we set y and z to 0, and so we get that the x-intercept is 3. Similarly, the y-intercept is 3, while the z-intercept is -3. After plotting the intercepts, we can clearly see the traces in the coordinate planes. Therefore, we have now sketched a portion of the parametric surface. In the next example, we want to describe the parametric surface S defined by R of uv equals u cosine v I hat plus u sine v j hat plus 4 minus u squared k hat. In addition, we want to identify all constant u curves and the constant v curves with v equals 0 and v equals pi over 2. As in the previous example, we start by writing parametric equations for S, which are x equals u cosine of v, y equals u sine of v, and z equals 4 minus u squared. We again arrive at a system of 3 equations, and we want to eliminate the parameters u and v to obtain a Cartesian equation of S. However, observe that the system we have here is nonlinear. Hence, eliminating u and v in this system is not as direct as in the previous example. In this particular case, we can square both sides of the first and of the second equation to get x squared plus y squared is equal to u squared cosine squared v plus u squared sine squared of v. Note that we can factor u squared on the right-hand side, and this leaves us with cosine squared v plus sine squared v, which we know from trigonometry to be equal to 1. Thus, we obtain that x squared plus y squared equals u squared. We can now substitute this expression for u squared in the third equation. This now yields a Cartesian equation for S, which is z equals 4 minus x squared minus y squared. Recall from Math 22 that the graph of this equation is a non-central quadric. Indeed, its graph is an elliptic paraboloid opening along the negative z-axis with vertex at 0, 0, 4. A sketch of the paraboloid is shown on the left. We now proceed in identifying all constant u curves of S. To this end, we set u to be the constant u0. We see from the third equation that z becomes 4 minus u0 squared, which is again constant. This means that the constant u curves must be the traces of the paraboloid on planes parallel to the xy plane. The blue curves on the left are some of those traces. Indeed, setting u equals u0 in the first two equations, we obtain that x squared plus y squared is equal to u0 squared cosine squared v plus u0 squared sine squared v, which simplifies to x squared plus y squared equals u0 squared. This is the equation of a circle on the plane z equals 4 minus u0 squared with center at the z-axis and radius u0. For instance, when u equals 0, we get the point 0, 0, 4, which is a circle on the plane z equals 4 of radius 0. When u equals 1, we get this circle on the plane z equals 3 of radius 1. And when u equals 2, we get this circle on the xy plane of radius 2. For the constant v curve with v equals 0, all that we need to do is to substitute v equals 0 in each of these equations. We get x is equal to u, since cosine 0 is 1, y is equal to 0, since sine of 0 is equal to 0, and still z equals 4 minus u squared. Note that substituting u equals x in the third equation yields z equals 4 minus x squared. The graph of the equation z equals 4 minus x squared with y equals 0 is the parabola z equals 4 minus x squared on the xz plane. Hence, the constant v curve with v equals 0 is the parabola colored teal on the left. Similarly, to obtain the constant v curve with v equals pi over 2, we substitute v equals pi over 2 in each of these equations. This time, we get x is equal to 0, since cosine pi over 2 is 0, y is equal to u, since sine of pi over 2 is 1, and again, z equals 4 minus u squared. Note again that substituting u equals y in the third equation yields z equals 4 minus y squared. The graph of the equation z equals 4 minus y squared with x equals 0 is the parabola z equals 4 minus y squared on the yz plane. Hence, the constant v curve with v equals pi over 2 is the parabola colored green on the left. For the last example, we need to find a vector equation of the portion of the cylinder x squared plus c squared equals 4 that extends between the planes y equals 0 and y equals 3 in the first octant. A sketch of the said portion of the cylinder is shown on the right. In the previous examples, we were asked to identify the surface defined by a given vector equation. Here, we are being asked to find a vector equation for this portion of the cylinder. In this example, we may choose x to be equal to the parameter u. Substituting x equals u in the equation of the cylinder yields z equals the square root of 4 minus u squared, where we take the positive square root since the portion of the cylinder is in the first octant, where z is non-negative. In addition, we should restrict the values of u to be greater than or equal to 0, since x is also non-negative in the first octant. Finally, we can simply set y equals v and impose the restriction that v is greater than or equal to 0 but less than or equal to 3, because the portion of the cylinder extends between the planes y equals 0 and y equals 3. Therefore, a vector equation of the portion of the cylinder is r of uv equals u, v, and the square root of 4 minus u squared, where u is greater than or equal to 0, and v lies in the closed interval 0 to 3. Observe that parametric equations or vector equations for a given surface are not unique. Indeed, we could have chosen y equals 2v with v in the closed interval from 0 to 3 halves. Another alternative is to set z to be equal to u with u greater than or equal to 0 and x equals the square root of 4 minus u squared. A significantly different parameterization of the portion of the cylinder is as follows. The fact that the curve x squared plus z squared equals 4 in the xz plane is a circle suggests that we can set x equals 2 cosine of u and z equals 2 sine of u, which clearly satisfies the equation x squared plus z squared equals 4. We impose the restriction that u is greater than or equal to 0 but less than or equal to pi over 2, so that we only obtain the portion of the cylinder in the first octant. Finally, we again set y equals v, where v is in the closed interval 0 to 3. Therefore, another vector equation of the portion of the cylinder is s of uv equals 2 cosine of u, v, 2 sine of u, where u is in the closed interval 0 to pi over 2, and v is in the closed interval 0 to 3. This ends the first part of the lecture video. Please continue and watch the second part of the lecture video, where we discuss vector equations of surfaces obtained by revolving a plane curve about a coordinate axis, commonly referred to as surfaces of revolution. Thank you for your attention and good day.